for today is by Sean Hartnoll. He's going to tell us about Wheeler-DeWitt states of the Schwarzschild AdS interior. Sean.
Did this do anything?
I think that works.
Perfect. Great. Well, thank you. It's a pleasure to be back in Swansea after many years. And so thanks to the organizers, Prem and Carlos. Very good. So I am going to talk about this paper that I put on the archive a few weeks ago. Okay, let's see. So there's several different motivations. So I want to explain the sequence of things that led me to writing this paper, but I think there were other possible motivations. So the context is AdS-CFT. And so in AdS-CFT, there's a boundary, and the boundary is a normal quantum mechanical system, and it has a time t. And so maybe I should even draw a picture. The boundary is time t. Now this time does extend. You can use the same formula that extends into the bulk, but as it extends, it gets redshifted because the bulk has a metric GTT. And this corresponds to the fact that if you're further in the bulk, things get redshifted relative to the boundary, and so they're more low energy processes. And that's the idea that in holography, the renormalization group gets geometrized, and things that are further in the bulk are the low energy, and things that near the boundary are the high energy UV processes. And so that's the essence of holographic renormalization. Now, at a horizon, GTT goes to 0, which is infinite redshift. Okay, and corresponding to that, consistently, study the horizon. Of course, everything is static, and GTT goes to 0, and then to see all the way to the horizon, you need to take t all the way up to infinity. And so you run out of energy, so you go all the way to the far infrared, which is 0, and at the same time, the boundary runs out of time, if you like. Right? You go to t goes to infinity. To get to the horizon. Now, of course, we know that in the bulk, there's something behind the horizon that is very interesting. It has singularities in it and things like that. And many people have wondered since the beginning of AdS-CFT, how do you see behind the horizon what's from the boundary point of view? On the face of it, it looks rather difficult because it's causally disconnected, and so they just don't know about each other. Okay. And so one line of thought has been sort of, this is an emblematic paper in this endeavor, but there have been others, which is to analytically continue the time coordinate. And there's a sense that when you go through the horizon, this boundary t coordinates gets shifted by beta I, beta over 2, or something like that. However, that's somehow something a bit unsatisfactory about that, especially in AdS-CFT, where there's another boundary where someone could be throwing things in from this other boundary. And so analyticity across this horizon is making an assumption about what's coming from the other side, and so you're not really learning about the horizon. You're just repackaging what's outside, inside, using the fact that Einstein's equations are second-order differential equations, so they have certain analyticity properties, and so the inside and outside are just connected. So analytic continuation is not really probing behind the horizon. Okay, you're just using facts that you know about outside in a clever way. I mean, sometimes it's a beautiful thing to do, but okay, very good. So now, but the bulk definitely does extend through horizons, and in the bulk, you definitely do not need to introduce complex time. Normally, you go to some infalling coordinates or something like that. And so, with that in mind, a couple of years ago, we were thinking about sort of, well, what happens if you just close your eyes and just continue the RG flow through the horizon? So finite temperature RG flow. And so you imagine at the boundary, what's an RG flow? Let's say you have a scalar field in the bulk. This scalar field will have some fall off near the boundary that's determined by the mass of the scalar field. For a particularly nice choice of the mass, the leading behavior near the boundary goes like R, and then there's a subleading mode that goes like R squared. R is going to 0 at the boundary in my conventions. And so this is the source for this. You source the scalar field at the boundary. Okay. Then the scalar field will have some profile that describes the renormalization group flow of some coupling due to the scalar field. But that flow just continues through the horizon. I mean, you just write down a deformation of the Schwarzschild, okay, and it doesn't stop. And a curious thing that we sort of emphasized here, not perhaps surprising a posteriori, but it's true, is that if you just keep going, as you go towards the singularity, you generically get some, well, you always get some scaling behavior. And so Schwarzschild, the Schwarzschild AdS has some behavior near the singularity. If I turn on a small source, the behavior near the singularity changes. Tau is the proper time to the singularity, and there's a scaling exponent, PT, that you can call the Käsner exponent, if you like. Okay, so there's an emergent sort of scaling near the horizon, near the singularity, which, has a bit the flavor of a fixed point, but it's not a fixed point because we've gone through the IR. Okay, so we called it a trans-IR fixed point. Okay, but we have no idea what it is, but we had no idea what it is, but it's there. I want to say something that also motivated this paper about the inside. So outside the black holes are very nice because they're stable. So if you're sitting outside the Schwarzschild black hole and you sneeze, okay, the air droplets will fall into the black hole will get a little bit bigger, and nothing much will change, right? If you sit here in Schwarzschild and sneeze, the future infinity is completely different from what it was, okay? So the inside of black holes are not stable, even though the outside is, and the generic approach to a singularity is some, chaotic, very inhomogeneous thing. So when you are probing the inside of black holes, you probably shouldn't take Schwarzschild AdS too seriously because it's not stable on the inside, even though it is stable on the outside. And so one motivation for this work was to just to show how easy it was to construct some very simple interiors that deform Schwarzschild. A very small deformation of the boundary changes the behavior of the singularity inside. Okay. Nonetheless, this left me feeling a bit unsatisfied because, what is this RG flow in the interior in the field theory without going to complex energies or something like that, which is a bit artificial. All right, so,
Sean, can I ask,
please.
Do you also worry about high temperature corrections as you go?
Well, of course, thank you. Of course, this boundary is not as nice as this boundary because it's very strongly curved. I mean, if you make n big enough, you can get as close as you want before you have to worry about the curvature corrections. But obviously, that's right. Yeah, exactly. So the hope, I guess, is that whether the scaling could be some organizing principle that actually helps you get a hold on these curvature corrections. But yes, important, yes, definitely. As you get too close to singularity, obviously there are going to be corrections. Thank you. Yeah. But you can have a parametrically big regime of the scaling within the classical theory. All right, so the first thing that is motivating this talk is that the right way to think about all this is Hamilton-Jacobi theory. So I'm going to go through a very slow reminder of Hamilton-Jacobi theory. I think, I'm sure many of you, of course, know what it is, but maybe it's not at the tip of your fingers. So I'll remind you how it goes. And the beautiful thing about Hamilton-Jacobi theory, so by the way, Hamilton-Jacobi theory is the classical version of the Wheeler-DeWitt equation. Okay, so that's why one reason we're doing it. But what's nice about Hamilton-Jacobi is that it's intrinsically relational, even in classical. So in classical mechanics, in Hamilton-Jacobi theory, when you solve for this, there's a function, S, right? And you solve for it at some point, and this S, what it does is it's going to relate, for example, x and p. So when you solve for a classical particle, you could find x as a function of time, or you could just find p as a function of x with no time in the equation. Right? And seeing as time is causing enough trouble with going through horizons, Hamilton-Jacobi seems like a nice formalism. It's relational. It relates x's and p's without talking about time. Okay, we'll see how it works in a second. And in gravity, for example, that means that it will give you, for example, the gxx coordinate as a function of gtt. They're both functions of r in Schwarzschild, right, are the radial coordinate, but you can also just think of them relationally. If I know gtt, what's gxx? Yeah? Okay. There's no time involved, or any other coordinates for that matter. And then also, of course, some constants of integration that, as we'll see, parameterize the phase space. Right. It's well known that Hamilton-Jacobi theory is the natural language for the holographic renormalization group. For example, this very early paper, nice paper by our Dutch friends. But because it doesn't depend on time, the zeroth other point I'm going to make is that it's a natural formalism to extend through horizons. So this is the picture. Don't worry about, we're going to come back to this picture later, so don't worry about the gray, the shading. So this was what I was drawing over here. Okay, there's a boundary time. You run out of time at the singularity, okay, so it's hard to go through. But this sort of Hamilton-Jacobi point of view, the boundary is where GTT goes to minus infinity, it's Lorentzian, and the singularity is where GTT goes to plus infinity, because time is spacelike inside the horizon. And you can just go, I mean, gxx is just a function of gtt, and it goes very smoothly from one to the other. There's no coordinate singularity because there are no coordinates, right? Okay. So that's what we're going to do. So let me, the next few slides, I'm going to talk about what Schwarzschild AdS looks like. Don't worry about this Wheeler-DeWitt stuff. We'll come back to that. And so let's see what Schwarzschild looks like from this point of view. So it's a very simple thing, but I think it might be useful to go through slowly. So this is going to be the theory. So this is gravity, negative cosmological constant, and the usual boundary term. We're in 4 dimensions because, you know, I like 4 dimensions. Okay. So we're going to make an ansatz. In the context of Wheeler-DeWitt, this is called a mini-superspace. It means we're restricting to some subset of possible metrics. But it's the most general ansatz that has a rotational symmetry in the x and y directions and a time translational symmetry in time. Right? So the boundary coordinates are t, x, and y. Right? Those are the boundary coordinates. And r is some radial coordinates. And I'm going to think directly about the interior. So the minus, I'm going to use little arrows to highlight bits of equations. So the minus sign r is the time coordinate, okay? Because I'm imagining that I'm inside. I'm looking for the solution inside. It'll go outside too, it doesn't matter. So then there are 3 functions, n, v, and k. N is the lapse. It's going to disappear very soon. V is the volume of this part of the metric, the spatial volume. And k is a measure of the anisotropy, right? It tells you how time is stretched compared to the x and y directions. There's a plus here, a minus there. These cancel when you take the determinant, and so the volume is fixed by this v. Okay, so it turns out this is a convenient way to parameterize this metric. So you take this ansatz, you plug it into Lagrangian, and you get this. Okay, so this k and v are functions of r, right? Everything's a function of r only. And n has no derivatives. It's a Lagrange multiplier. It imposes a constraint, right? As many of you know, analogous to Gauss's law, okay? And it's called the Hamiltonian constraint. All right. So so the equation of motion for n is this Hamiltonian constraint. And here I've also expressed it in terms of momenta, right? So pi of k is the momentum conjugate to k. And so you differentiate the Lagrangian with respect to dr of k, and the momentum is something like this. Okay, so. Yeah, so this is the Hamiltonian constraint. And so, so the Hamilton-Jacobi equation is what you get when you take all the pi's and you introduce a function s that's a function of the coordinates. So s is a function of v and k. Note that k has dropped out of this equation. That's why k is a nice coordinate. S is a function of v and k, and you replace the pi as ds di, right? So pi k becomes dk of s, right? That's how you get, but this is the Hamilton-Jacobi equation in this context, which are supposed to solve for s, yeah? So, and it's important when you solve the Hamilton-Jacobi equation that you get enough constants of integration, okay? In this context, it's enough to get one constant of integration, not the trivial one. Obviously, you can shift s by a constant, and that drops out. That one doesn't count, okay? So it's very easy. You can actually more or less do it by I, right? There's a something squared minus something squared. So the solution of this is given in terms of a singe. So we have the solution for this S. It depends on V and K. Those are the metric data. And it has a constant of integration, K0. So the volume, singe, K, and there's the constants. Okay? All right, so now what do we do with this? If you remember back to your whenever you last thought about Hamilton-Jacobi theory, what you're supposed to do with this solution is differentiate it with respect to the constant and set that equal to another constant. If you don't remember that, this comes from doing a canonical transformation that trivializes the Hamiltonian. Okay? But we'll also see in a second that this arises as a saddle point approximation from a WKB wave function. Okay, so this really comes from quantum mechanics, as we'll see in a minute. Anyway, this is what you're supposed to do. That's what the textbook says to do. You take it, you differentiate with respect to the constant, and you set that equal to another constant. And then this, you now solve for v as a function of k. All right, so now this is relating one coordinate and another coordinate, and they're two constants of integration. Okay? This is, in fact, just a Schwarzschild AdS solution. Right? So if you write down the Schwarzschild AdS solution, the volume of constant r slices is related to the anisotropy in exactly this way. And you can do a change of coordinates if you like, and you'll find out that this is, okay, so this is the Hamilton-Jacobi derivation of Schwarzschild AdS, okay? There's no time here, right? It just relates V and K, right? It's like relating P and X for a particle, or X and Y for a particle. And these constants of integration parameterize the phase space of solutions, the natural coordinates on the phase space of solutions. So let's just understand this solution. So for a given K0 and epsilon 0, K runs from -infinity. This is the interior. It's clear that these coordinates are not going to be good. Well, I'll come back to this in a second. So from -infinity at the horizon to +infinity at the singularity. And as a function of that, this sec is one of a singe, right? So or one of a cosh, sorry. And so it goes up and down, right? So V has a maximum. And in fact, it's well known that planar Schwarzschild AdS, the volume of the interior slices has a maximum. Okay. So this is a relational, timeless formulation that relates symmetric degrees of freedom without referring to any coordinates explicitly. Yeah?
Sean, question?
Yeah.
Could there have been like P, pi sub V in that formula? Or?
Here, no. So S is a function of V and K. Now you can get the pi's by differentiating S with respect to V or K.
Okay.
Right?
This always gives you just the coordinates.
But this, yeah, that's right. It doesn't depend on pi's. Yeah, that's right. Okay. Any other questions?
This ansatz, do you have much control of deviations away from that ansatz?
Yeah, sorry, say again, what was the question?
So you pick this particular ansatz, which is rotational symmetry. Do you have much control of deviations away from that ansatz?
Well, I mean, I haven't even thought about it, but yes, of course, you can take a more general ansatz and plug it in. Obviously, the more stuff you have, the harder it is, yes. But actually, because the interior, as I told you, is generically very inhomogeneous, it's going to be important to go away from this ansatz at some points. Yeah. Okay, so I wrote S in terms of V and K, but we could also take the same function and just write it in terms of GTT and GXX, right? So there's some trivial relation between them, right? So GTT is V to the 2/3 times E, right? It's just this thing is GTT, and this thing is GXX, right? So we can just write the same function in terms of those coordinates, right? The same function, and the signs, etc., becomes this. Right. And so this is not the solution, right? And then you get the solution by differentiating with respect to K0, and you call that epsilon 0. That this is the same as before, but now so this now is the relational solution that gives you GXX given GTT. So let's see how that works. So now we can go, look, it's linear in GTT, okay? It's pretty nice. So we can go near the boundary. So that's GTT goes to -infinity. If you solve for GXX in that limit, you find the leading order term is GXX goes proportional to GTT, which is true in AdS, right? And we see that the constant K0 is some normalization of time. You can go to subleading order, and turns out is the correct behavior, and this lets you identify this epsilon 0 is in fact the ADM energy of the solution, which makes sense that the energy is sort of conjugate to the normalization of the boundary time. Okay, so it has the right behavior, that's what I'm showing you. And if you take GTT to +infinity and solve for GXX using this equation, you find that GXX now goes to 0, it collapses, and GXX goes like 1 over GTT squared, and in fact that's just this Kästner scaling, this Schwarzschild. It's a special case of Kästner. Okay, so these two different scalings are just both. So this, you can certainly go from the boundary to the horizon with this formula very, very simply. Okay, very good. So Wheeler-DeWitt is now just the canonical quantization of this Hamiltonian constraint, right? Meaning that you take all your momenta, pi of k, etc., and you replace them with ddks, just like you do in quantum mechanics. And so then you imagine that there's going to be a wave function, psi of k and v, and so this is this mini superspace, right? It's really a slice of a much bigger wave function for all possible metrics. So it's a wave function of k and v, or GTT GXX, and this is the Wheeler-DeWitt equation in this context. Of course, when you quantize something, there are ordering ambiguities, right? So like p times x is not equal to x times p in quantum mechanics. So this is some canonical choice of ordering. It doesn't matter too much in the semi-classical limit, which is all you should really trust anyway. Okay. So this is the Wheeler-DeWitt equation, and it's instructive to just solve it. Okay, so this is supposed to tell you something about, right, so maybe I should say something about how you're supposed to think about this. There's no time in this equation, right? And so for the interior, you're supposed to imagine these different slices. Okay, those different slices all have different metrics, different induced metrics on them, and you're just in the interior. This wave function is a wave function of the whole interior. And what it's supposed to give you is something like, well, suppose I measure the volume, okay? I have a state, and then I ask, what's the volume? It's supposed to give you the probability of finding different slices of where you are, okay? So it's a time, it doesn't describe evolution in the interior, it describes the whole interior. It's a state, it's a wave function. And so different volumes, the volume, for example, is one of the things that has an expectation value. Different states have different expectation values, which will correspond to finding yourself on different slices in the interior, for example. Okay. There's no time. Okay. So this equation is simple enough that even you can solve it. Actually, in fact, if you just plug it into Mathematica, you'll get some Bessel functions, but this is not the nicest way to write it. And so the general solution to this equation can be written as follows. So firstly, kappa is so basically Fourier transform in K, and then you get a sort of first order equation. Kappa bar is going to be a constant of integration. This is a whole function that you get to choose of this constant of integration. Kappa bar is a parameter. This is a whole function that you get to choose. And then there's an exponent e to the is of v and k. This thing's a function of v and k. And k bar, which is just the k0 that we had before. I'm calling it k bar now because I'm integrating over it. And this is exactly the Hamilton-Jacobi function that we had before. Okay, so when you think of a semi-classically as a wave function of being e to the I, the action, right? The Hamilton-Jacobi function is just the action on shell as a function of the boundary data, which are v and k. And for this equation, it turns out this is actually an exact solution. Okay, that didn't have to happen, but it does happen here. And so now this constant of integration, when you build the wave function, you can integrate over it with an arbitrary weighting. It's like building a wave packet, right? You have e to the I k p0, and then you integrate over p0 and you make a wave packet out of it. Okay, so it's the Hamilton-Jacobi function, and then this is the wave. Okay, so yeah, you could write it in terms of Bessel functions, and the semi-classical wave function turns out to be exact, and there's a plus and minus here. So this is just the most general solution to this equation, and it depends on one arbitrary function. Okay. Yes.
K bar is replacing your K natural, still with
Yes, that's right. It's
mass interpretation.
so good. Let's see. So at the moment, there's only one constant, right? So this s, this is not a function of two variables. We'll see where epsilon comes from in a minute. But at the moment, that's an important point. At the moment, there is only one constant of integration. S only depends on one of the constants. Yeah. Very good. Yeah, good. Actually, that's a good question. I don't know. But it is true. But actually, I don't know. So in case this helps you, this particular equation has been studied quite often in terms of scattering. So you see how there's a v ddv here. So if you change this to like a capital V, then this becomes an exponential potential. And so this is like Schrödinger equation with an exponential potential. Okay, maybe there's a known reason why WKB is exact in that. So this comes up in Liouville theory and also in JT gravity. So yeah, it's the same equation that people solve in Liouville theory. Yeah, all right. Okay, so let me just remind you about a few things but let's think of it as a WKB wave function. That's all we should be doing, because clearly this is not the microscopic theory of quantum gravity anyway, right? Okay. Good. So these states are delocalized, right? Just like, so say if you do a WKB, when you solve WKB in a wave for some potential, you find a scattering state, right? Which are these plane waves. But of course, WKB is the classical limit, but a particle moving around is not a plane wave, right? It's a wave packet that you have to build out of the plane waves. Okay? So if we want to recover the classical universe from this wave function, we have to build a wave packet out of it. Just as if you want to recover a classical particle from a WKB wave function, you also need to build a wave packet out of it, all right? So these basis states are delocalized, right? So they're like uniformly supported, for example, along in the interior. That's not a classical universe, okay? So to recover a classical solution, you need to build a wave packet. And so this is the reason I introduced the k-bar. K0 is going to be the expectation value. We're going to build a wave packet that's peaked on k0. So I'm going to use k0 for the classical value where the wave function's peaked. So to build a wave packet, of course, there are many ways you can do it. So we're going to take this function to be a Gaussian. Okay, so delta is the width of the Gaussian. It's localized at k0. And when we build this wave packet, we're also going to introduce a phase that we call epsilon 0. Right? This is the phase. This is linear in this thing, and there's a phase there. Okay, you certainly have the freedom to do so. It's a wave packet, right? It has a width, a location, and a phase. All right. It's the same thing. So if you were doing a particle, you would also have an e to the I e here. Okay, it's the same thing. If in this limit, so it turns out, well, so you want your just like in quantum mechanics, you want your wave packets to be narrow but not too narrow. Because if you make them too narrow, then the momentum, the conjugate variable, starts getting delocalized. So if the width is in this range, then one can check that this integral, and in particular expectation values, which I'll tell you about in a minute, that involve basically integrals very similar to this one, you can evaluate them in a saddle point approximation when epsilon 0 is large, and they're peaked at k0, and the variance is small, that the wave function, okay, so we'll get to that in a second. So it's natural when epsilon 0 is large, which it is here, to do a stationary phase approximation on the integral. And when you do that, the saddle point, so you're integrating over k bar, right? So the saddle point is ds dk bar, which was exactly what was in the Hamilton-Jacobi stuff, right? You differentiate with respect to the constant, right? ds dk bar is equal to d dk bar of this thing, right? d dk bar of this thing picks out this epsilon. This term is 0 because the wave function is very strongly supported at the peak of the Gaussian, and so all integrals that you do are going to be dominated by k and v that obey this equation, which is the classical equation of motion. Okay, so I'm not telling you anything that you should not have already known from WKB. Right, write down a WKB wave function. You build a wave packet out of it. All expectation values are calculated by the classical equation of motion via the Hamilton-Jacobi equation. Okay, which is, but crucially involves, now there are two constants. And you can check that expectation values, I'll tell you how to calculate them in a minute, obey the classical equation of motion. And in particular, if your wave packet is narrow enough, you can go close to singularity and nothing, the classical equation of motion still holds. So to give you let me tell you a little bit about how to calculate expectation values. How am I doing? Yeah, that's good. So I think this is a very nice thing which maybe some of you may know from the old days, I guess. So, right. What are expectations? For the expectation value, you need an inner product, right, and a norm. Okay, so where's that going to come from? So the Wheeler-DeWitt equation is a Klein-Gordon-like equation, and it does have a conserved norm. It has a conserved charge, but it's not positive definite, right? It's just like in quantum mechanics, where there are quantum field theory, where there are particles and antiparticles. However, the modes can be split into positive and negative norm modes. That is basically this plus minus is in the way, right? It's the flux. The norm is the flux, and the flux can go one way or the other way. Traditionally, what is done is what these are, and it's natural to associate these different signs with the sort of future interior and the past interior. So in cosmology, that's like an expanding universe and a contracting universe. Okay. And so then you can just project onto the states, it's a subspace, that have a definite sign under this inner product. Okay, we'll see what this means in a second. So you restrict to sign definite states, then you have it in a product, and crucially, because of it's conserved. Okay, so what you do is you under what, right? So we want to have quantum mechanics. I want to have probabilities, right? I want to have a probability of finding the universe in some states, but that probability should not change as a function of time. Okay, but there is no time. All right. So what you do is you choose one of your variables as the clock, for example, GTT, and you declare, I know GTT. All right. And then I ask, what's the probability now of finding a given value of GXX, given that I know GTT? It's a relational probability, okay? And the Wheeler-DeWitt equation, in short, the norm that for any choice of variable, you can integrate across a corresponding slice in superspace, and the norm will be conserved. So let me give you an example. Suppose you know K, right? K was this anisotropy. So we're going to think of that as the relational clock. So given that I know K, I want to ask, what's the volume of the universe interior? Okay, so you can write down the following norm, which is now an integral over V, okay? And so I'm thinking of the wave function, sorry, this is the norm of the state, where I'm treating K as the clock, so it's known, it's a number, okay? And I write down, this is the norm of the state, where I integrate psi over V. And I can check using that this doesn't depend on K, right? So it's conserved, DDK of this is 0. So this is a norm of this state that doesn't depend on K, right? So it's conserved. So the state depends on, this psi depends on K, right? Things are evolving in K, but the norm is conserved. So probabilities are conserved, which they had better be, okay? So the Wheeler-DeWitt equation has enough structure to let you define relational clocks that give you a norm and probabilities that are conserved. Okay, so it's unitary in that sense, right? Okay. But you could then, using this norm, you can calculate expectation values. So for example, the expectation value of the volume using K as the clock with this Gaussian wave packet that I wrote down before, using this in a product, you can just do the integrals in the saddle point way that I just told you, and you'll get this. And this is the classical equation of motion, right? And so it does depend on time, right? The probabilities don't depend on time, but expectation values depend on this K, and these are the constants. Yeah? And so as long as you're in this regime, the quantum variance is found to be uniformly small in K. So basically everything is just, it really is classical in that limit. The Hamiltonian is pi of K, right? Because I'm thinking of K as time, so the operator generates time translations in superspace, right? This is not T. It's pi of K, and on the Gaussian wave packet, that's just epsilon 0. So actually, this epsilon 0 has a double life. It's the ADM energy at the boundary, but it's also the, quote, energy of the interior with this choice of clock. But you can choose many other clocks. The volume could be the clock. The extrinsic curvature of your slices could be the clock. Okay, there's not a preferred clock, that's a good thing. So another example that's going to be useful is that you could think, well, maybe I can treat GTT as the clock. And in that case, so psi, if I know GTT, the norm's a bit more complicated. That's why K is nice. That's why I introduced K to begin with. But you can check that if I differentiate this with respect to GTT, it vanishes. Of course, this is with some assumption about the fall off of the wave function and so on. Yeah, please.
Yeah, since you are giving this second example, I already wanted to ask whether there was any general structure in the original Wheeler-DeWitt.
Yes, of course there is. Yes, absolutely. Yes, there's a J mu.
So basically, when you say that there are different clocks, which is great, that there is always a well-defined algorithm that gives you this concept.
Yeah, absolutely. I just like down to earth person. Yeah. So there's a current in superspace that's conserved. These are just.
Okay. So you are using more or less the standard Klein-Gordon kind of.
Yes.
Okay. Good. So
No, thank you. No, it's important. Yes. It just, to me, it makes more sense when I just see it. But yes, it's general. I'm not making it up as I go along. That's right. Oh, it's like, it's the, it's Q0. So if you have a J mu, so if it's J0, is that the time? Yeah. So N, so yes, N dot J or something. Okay, so now a comment. I don't have anything very deep to say about singularities, and I'm pretty sure this point has been appreciated a long time ago, but let me say it anyway. I mean, part of the reason to be thinking about all this is to understand the singularity a bit better. A scary thing about space-like singularities is that time ends. Okay, what does that mean? Is that, but I mean, so it seems natural that what better framework to think about these singularities where time ends than a framework where there's no time to begin with, right? Time can't end if it's not there. Okay, so the end of time is simply a limit to the relations that can exist, right? So you have x and p's. Given x, you know p, and so the universe is a series of possible relationships, and some relationships are just not possible. They don't arise, and that's fine. Okay, okay, yeah, very good. So yeah, so a bit more on this timeless state, and then we're going to connect to the boundary. We're nearly, yeah, very good. All right. So this interior state is timeless, and what I've just been telling you is that the structure related to the previous question of the Wheeler-DeWitt equation is sufficient for a relational clocks to make sense at a quantum level, and it ensures the existence of a conserved positive probabilities associated with any choice of clock. Okay. So an idea for the future, what would it mean to resolve a time-like singularity? So to resolve a space-like singularity, there's some degrees of freedom, stringy degrees of freedom become important at the singularity. For a time-like one, I think what we should do is write down a wave function that's not only not minisuperspace, it's not a wave function of the metric, but is a wave function of some matrix degrees of freedom or some stringy fields. Maybe there are these pre-existing ideas about tachyon condensation, their singularities and stuff. There should be a wave function, a timeless wave function that just describes the interior, including the singularity, that would include some stringy, because as Kostas was saying, clearly, presumably stringy or some microscopic degrees of freedom become important near the singularity, and so they should just be in the wave function. Okay. Now, I want to make a point related to other work. So the Hilbert space of this interior that one builds using this Wheeler-DeWitt is not the same Hilbert space as this boundary one, right? Because it's sort of self-consistent. So another thing you could do is try to make slices. Many people have done made good use of this fact that you can make a slice that goes to the boundary, and slices that go to the boundary inherit a time from the boundary clock, right? And so that was this picture. So if I have the boundary and I have a slice that goes across like this, then there's a causal patch that's sometimes called the Wheeler-DeWitt patch. And this patch is a function of time, right? And so there is a Wheeler-DeWitt equation just for the bulk that directly maps onto the Schrodinger equation on the boundary in principle, right? But that will describe this patch. But what I'm talking about is something a bit different, where you're sort of in the interior, and there is no. I'm trying not to make use of this time. However, this Wheeler-DeWitt patch, as t goes to infinity, does become this patch here. Okay, so there may be a sense in which this interior state is the t goes to infinity state of some boundary field, of the boundary field theory. I'm not sure. Okay, because you've run out of time. Right, as I was emphasizing, but that's fine. There is no time in the interior. It's just a state of being. Okay, very good. Okay, so now I talked about GTT as the clock. Okay, so this Wheeler-DeWitt equation I've been talking about so far has been here. But as I emphasized in the classical discussion, you can certainly take GTT outside of here. And so now let me talk a little bit about what would happen if we just take this wave function, okay, this thing that we wrote. Right, this is an explicit wave function of v and k, given a choice of this wave packet. So we could also write that as a function of GTT and GXX. They're trivially related to each other. Let's take GTT to be the time, and let's just take the wave, and let's just take GTT to be negative and see what happens. Okay. So GTT can be extended to negative values. These correspond to the exterior, and GTT goes to minus infinity as the AdS boundary. Right? So it turns out that it's quite nice, and perhaps not surprising. So as GTT goes to minus infinity, the Wheeler-DeWitt wave function evolves into the boundary Lorentzian partition function. But actually, let me, before showing you that equation. So now we're slicing in terms of, radial slices instead of time-like slices, okay? But here, this idea of fixing, so the same, how can I say it? You have an object that's a function of data along a slice, and that's exactly what this boundary holographic RG flow boundary partition is, right? It is the Wheeler-DeWitt equation run sideways. That's what Verlinde and de Boer said many years ago. Okay, so it's the same equation. So exactly, the boundary partition function also obeys, as a function of boundary data on slices, also obeys the Wheeler-DeWitt equation going along here. And in particular, but you could ask, okay, so hopefully it's very reasonable, right? That the state, the Wheeler-DeWitt equation just evolves the state into a partition function. It's very natural because the partition function is a function of boundary data. But you could ask, what about this function beta, right? There was a whole function's worth of ambiguity in the state, which is maybe less familiar in a partition function. But actually, it's a nice. So the way it works turns out to be that this state, okay, the wave function that we wrote down before, which depended on GTT, GXX, and it had a whole function's worth of sort of phase constant of integration. If you just integrate it using the Wheeler-DeWitt equation through outside and all the way to the boundary, you still have this integral over k. There's a weighting of this k, and this is a partition function weighted by time. This is like a time evolution of the boundary Hamiltonian in a background metric, uniform, GTT and GXX are constant, by some time k bar. Remember, k bar is like k0, and right at the beginning when we wrote down the Schwarzschild, remember k0 is appearing here as sort of the normalization of time. Okay, so it comes back again here. Just, I have a proper argument in the paper, but roughly it goes like, remember epsilon 0 was defined as sort of the conjugate variable to k bar, and we saw that epsilon 0 was the ADM energy, and so, okay, maybe it's reasonable, not too surprising, it's the e to the I k bar. This is basically epsilon 0. Okay, it's like the energy. So this is a partition function that has a weighting under, it's a weighted partition function, okay? Which is clear. Let's put in the Gaussian. Now, for example, to make this very clear, let's put in the Gaussian beta. So if you put in the Gaussian beta, you do the k integral, and so this state, I think I've put k0 to 0 here. So this is the interior state on the Gaussian wave function with width delta and phase epsilon 0. I've set k0 to 0 just to make it shorter, is trace, becomes the partition function of the boundary theory with a Gaussian weighting. So this is the partition function over some energy window of width delta centered on epsilon 0. To make it even more explicit, just using the actual form of this for Schwarzschild and extending it to the boundary, it's exactly this quantity. So you integrate over all energies. The energies are supported near epsilon 0. So there's a spectrum, right, in the boundary theory. There's some density of states. There's an energy. There's a window with delta. And there's a partition function. It's counting all the states in that window. It's a very natural thing. Smeared. It's very natural to smear. So this is literally what you get by taking this wave function and taking it to the boundary. So this is Gaussian weighting of energies, and this is the density of states that is expected in the 2+1 CFT. It comes out of the Schwarzschild solution. So more generally, you pick your state in the interior, you run it out, and it will give you some partition function on the outside. And there isn't a preferred state. So a lot of the literature from the 80s is arguing over what was the initial condition of the universe, okay? And maybe that's correct. I mean, presumably there was an initial condition, but in this context, different states are just different choices of partition functions here, okay? And of course, some might be nicer than others, but in principle, you could pick whichever one you want. Right. Okay, so to end. So the first point I made is that evolving boundary quantities as a function of the background metric, GTT, rather than time, might be a promising way to probe the interior, including the singularity. This discussion does have some flavor of the so-called TT bar or T squared deformations. It may be related. And then the second point is that the eternal AdS black holes are very well-grounded settings for anything involving quantum gravity, and in particular sort of cosmological questions of the interior using this Wheeler-DeWitt states should be should be a good starting point for thinking about that. Okay, thanks a lot.
So where is the signature horizon? What happened? Why is DTP equal to 0?
That is an excellent question. I'm not sure, but I can. But actually, so yeah, very good. So something. Yeah, I'm not sure actually. So it's true that. Yeah, GTT vanishes. Yeah, that's not a very special point. So like the.
There must be something that doesn't allow you to shift it with coordinate.
I mean, I should say this continuation outside. I mean, it has an element of formality to it still, in the sense that we wouldn't normally think of this as a wave function. But well, okay, something else you could definitely do. The short answer is I don't know, but thinking out loud, I mean, something else you could do that. So what I've been doing has been implicitly symmetric in these two sides. Of course, I could have sources on this side that don't appear on this side. And then I could make something happen at the horizon, right, by throwing in things from one side. And so I could definitely imagine how the horizon would appear as a natural point, but I must say it does not, yeah, it's a good question.
When GTP is 0, GXX is infinity, is Hamiltonian energy all that?
No, GXX isn't, no, GXX is a constant at the horizon. It's GRR, but there is no GRR. Yeah. Yeah, things don't blow up. Nothing blows up at the horizon, which it shouldn't. I mean, right? Yeah. So that's right. So yeah, maybe the horizon. Maybe you do need these both, because the horizon is a bit of a teleological concept, as we know. So perhaps. Okay, I'm not sure. The question would be, what's the simplest thing that reveals the horizon to you as a special place? And I'm not sure.
The GRR was the function n that you use as a Hamiltonian to get the Hamiltonian.
Yes, that's correct. Yes.
So is there any subtlety there with the Hamiltonian?
It's a good question. Not that I've run into yet. This might also be known from the old days. But by the time, yeah, it's a fair question. Because once you get to here, it's just gone. And you don't need to solve for it. In fact, it's a gauge. In fact, yeah, it's a gauge redundancy. So another way to say it, perhaps that divergence is a gauge artifact in some sense. So as far as I'm aware, I've not seen a subtlety there. Yeah.
You began by emphasizing that classically you have different things happening on the inside of the horizon correspond to the same outside.
Yeah.
Can you see that?
Yeah, I think that I think this is I think it comes back to this thing that to explore that you should consider, you could ask what kind of states do you get when you put a source on one side and not the other side? And I haven't actually thought about it, but I've thought about thinking about it, which is why I mentioned it, yeah. I think that is definitely doable within sort of some the OTOC, sort of some version of OTOC stuff.
You just modify the answer. So.
Yeah, I must say I have not thought more than what I've said. Yeah.
Sorry,
So your Wheeler-DeWitt wavepacket equation is like a wave equation with attention. It looks like, yes, that's a wave equation with attention, which is K independent, so that must be taking certain energy to
Yeah, exactly. So that's right. So there's some extra structure in this equation, which I think there won't be most of the time. So that, yes, that's right. It's actually, well, it's pi of k, right? And so that's the energy for the k clock, if you like. And so that the reason that this thing came out time independent, it doesn't always have to. So you pick your clock, there's something that generates shifts in that. The expectation value of that Hamiltonian will be time dependent most of the time, and it isn't here. So it's, okay. Say a second.
should be something like a K-derivative inside.
Yes.
Whereas the conserved energy from that equation would be quadratic inside.
No, that's good. No. So inside, no. So this expectation value is quadratic inside. Right? You like sort of put it here and here, and actually it is actually it's yeah. It's like actually I have that expression right. So it's sort of this term squared plus this. It may have a deeper, but okay, that's what it is.
So you're essentially solving the Wheeler question, which is integrable. What is the interpretation of this integrability on the graph?
I don't know. It's probably related to the fact that this ended up being exact, but this is this is a subsector of the theory that's definitely not integrable. So I don't know, I wouldn't want to lean too heavily on. I can certainly solve the question.
Can you compute expectation values of local fluctuations?
Yeah, no, I think that's the next thing to do really is to go away from this. Like, so for example, cosmology, in a quantum cosmology context, one thing that people do is you have like de Sitter and you put some inhomogeneities on top of it and sort of as perturbations. And so let's say you could have a situation where the wave function is dominated by, let's say, the scale factor, the sort of classical, but then you have some sort of quantum fluctuations on top of that, and you can definitely do that here. I think it would be interesting. One thing that is not so nice, so in cosmology, the universe gets big, and so the fluctuations are small, whilst here everything's crunching, and the fluctuations are actually a leading order effect. I mean, they should be important. But in principle, definitely. No, I mean, within this, I don't think there's any local information, but you could definitely add it.
So at the start, when you make your ansatz, are you assuming K and B are just spatial functions at the beginning?
Yes, that's this minisuperspace, that's right.
What, I mean, for more general solutions to Einstein equations, right, they could will be time dependent, or you could have more general ansatzes. So
Absolutely. Well, not time. Of course, yeah. This is some, in general, the Wheeler-DeWitt equation is some extremely horrible functional differential equation, right?
yeah. So I guess what's the interpretation of that in terms of the wave function picture then? There's just some state.
So I think a useful way to think about it. So if you're just doing gravity and you haven't tried to do string theory or some matrix thing that you might hope to be exact, if within old-fashioned Wheeler-DeWitt, you could think of it as you should really only go to semi-classical level, presumably. Okay, so I think it's just a way of doing. It's an alternative way of doing semi-classical gravity. But it might be well suited to sort of cosmological type questions. But it's not different. In principle, there should be a map between the Euclidean, functional determinant type methods and when you do WKB, you get this, and then there's some. Here there happens not to be, but normally there's some kind of determinant that would go in the front, right?
Yeah.
And so.
I guess that would be different.
Well, sure, yeah. If things are space dependent, yes.
Yeah.
Yeah. So I think Wheeler-DeWitt by itself does not really buy you more than, say, semi-classical Euclidean quantum gravity would. Okay. However, it may be a useful conceptual starting point for certain questions, such as spacelike singularities. Thanks, guys.